In this video here, we're going to take a look at tangents and normals to an ellipse. Now we can easily find tangents and normals to an ellipse by using either parametric differentiation or implicit differentiation. And we'll also shortly give the general equations for tangents and normals to an ellipse, but it's recommended that you derive the results yourself when working through problems rather than trying to memorize the formulae. So let's introduce the general equations for a tangent and a normal to an ellipse. So let's introduce here the general equations of a tangent and a normal to an ellipse. So starting off then with an equation of the tangent here. So an equation of the tangent to the ellipse with this equation here. So just our standard equation for an ellipse, right? At this point here, P, so just a general point on the ellipse then. So that's A cos of t, B sine of t is given as the following here. So as you can see then, we get the following here. So I get AY sine of t plus bx cos of t, and that is equal to AB here. So that's an equation of the tangent to the ellipse, but what about now an equation of the normal? So for an equation of the normal here to the ellipse with this equation, just the exact same as what we had here. Again, at this general point P, right, so A cos of t, B sine of t is given as the following. So as we can see then, we get AX sine of t minus BY cos of t is equal to a squared minus b squared times by cos of t times by sine of t. Okay. Now, as we've already mentioned, right, don't try to memorize these formulae, but it is important that you're aware of what they would look like. Okay. So equation of the tangent here and equation of the normal. So in terms of an introduction here to tangents and normals to an ellipse, we don't need too much more than that. So let's just take a look then at two practice questions here. So let's just get started here then with question 1. So for question 1 here, as we can see, right, we just want to find the equation of the tangent to the ellipse with this given equation here at the point P, which has the following coordinates. We have 4 cos theta and 2 sine theta. So the first thing that we need here is dy by dx. Okay. So we need dy by dx, and there's two ways to obtain this here. So method 1 would be to use implicit differentiation, and method 2 would be to use parametric differentiation. Now, I personally prefer parametric differentiation, so that's the method I'll use throughout this video here. But if you do prefer implicit differentiation, that's absolutely fine. Okay. Either way, we should get the same answer, obviously. So in that case, then for parametric differentiation here, we get dy by d theta, and that's all over dx by d theta. Okay. So x here, so x is equal to 4 cos theta, and y then is equal to 2 sine theta. Okay, so in that case then, dx by d theta, so just differentiating x here with respect to theta, hopefully nice and straightforward. So dx by d theta. In that case, then we simply get minus 4 sine theta. And then for dy by d theta, what I get here is 2 cos theta. Okay. So for dy by d theta then, that is 2 cos theta. And that's all over dx by d theta, which we just evaluated as minus 4 sine theta. So obviously we can simplify this here, right? We get cos theta or minus cos theta all over 2 sine theta. Okay. And we don't need to do anything further here, right? Because all we're looking for is the equation of the tangent to the ellipse with this given equation here. We need to take the negative reciprocal of this then if we wanted the equation of the normal, but because we're just looking for the equation of the tangent here, this is absolutely fine. So this here then is our gradient. Okay. So now what we're going to do here is use the formula then for the equation of a straight line. So we're going to use here y minus y1 is equal to m, that's our gradient here, which we just evaluated, times by x minus x1. Okay, so y1 here is 2 sine theta and x1 is 4 cos theta. So hopefully from here on out then, pretty straightforward. So what do we get here? I get y minus then y1, that's 2 sine theta. We get y minus 2 sine theta is equal to m. So that's our gradient here. So we get minus cos theta all over 2 sine theta, like so. And then we times this here by x minus x1. So x1 then is 4 cos theta. So we get x minus 4 cos theta. So what should we do next? Well, let's just times through by 2 sine theta, right, to get rid of this fraction here. So in that case, then we get 2y sine theta. So 2y sine theta, like so. We then have minus 2 sine theta times by 2 sine theta. So in that case, then we get minus 4 sine squared theta. Okay. And this here then is equal to minus cos theta times by x. So I get minus x cos theta, like so. And then minus cos theta times by minus 4 cos theta. Just be careful with the signs here, right? I get plus, so plus 4 cos squared theta. Okay. So let's just do a little bit of rearranging here. So I'm going to get x cos theta. So x cos theta plus 2y sine theta. So plus 2y sine theta is equal to 4 sine squared theta plus 4 cos squared theta. So 4 sine squared theta plus 4 cos squared theta. Okay. So clearly here then on the right hand side, we can factor the 4 out. So I get x cos theta plus 2y sine theta is equal to 4 lots then of sine squared theta plus cos squared theta, like so. And clearly then we know that the value here of sine squared theta plus cos squared theta is 1. So we get 4 times by 1, which is just 4. So in that case then, the equation of the tangent here to the ellipse with this given equation would simply be x cos theta, so x cos theta plus 2y sine theta is equal to 4 there. Okay. So this here then is the equation of the tangent to the ellipse with this given equation here at the point P. Okay. So there we have it then. Let me just quickly highlight this. So this here then gives us the solution to question 1. So let's have a go now at the very last question here. So for the very last question, then question 2, all we want to do is find the equation of the normal to the ellipse with this given equation here at the point P, which has coordinates of 3 cos theta and 5 sine theta. So the first thing that we need to do here then is find dy by dx here. And to find dy by dx here, right, we can do this in one of 2 ways. We can either just use implicit differentiation or we can use parametric differentiation. And again, just as I did for the previous question here, I'm going to use parametric differentiation. So what I get here then is dy by d theta, and that's all over dx by d theta. Okay, so x here then is equal to 3 cos theta, and y here is equal to 5 sine theta. Like so. So in that case then, dx by d theta here, nice and straightforward, right? That would be minus 3 sine theta. We get minus 3 sine theta there for dx by d theta. And now for dy by d theta, what do I get here then? Well, this would simply be 5 cos theta. Okay, nice and straightforward there. So we now have everything that we need to find dy by dx then. So in that case, dy by d theta, that gives us 5 cos theta. And that's all over dx by d theta, which is minus 3 sine theta. Minus 3 sine theta. Okay. Now do be careful here, right? So we'd use this to find the equation of the tangent, but we want the equation of the normal. So what I need to do then is find the perpendicular gradient. Okay. So for the perpendicular gradient here then, all we do is we flip this fraction here and times through by -1, right? It's just a negative reciprocal. So in that case then, what I get here is 3 sine theta. So I get 3 sine theta all over 5 cos theta. Okay. And at this point now, all we're going to do here is use the formula then for the equation of a straight line. So we're going to use here y minus y1 is equal to m times x minus x1. Okay. So putting that all together then, where this here is equal to m, and x1 is 3 cos theta, and y1 is 5 sine theta, what we get here then is y minus 5 sine theta, and that is equal to m times x minus x1. So m then is 3 sine theta over 5 cos theta. So 3 sine theta over 5 cos theta. Okay. We times through here by x minus x1, where x1 is 3 cos theta. So 3 cos theta there, like so. So now let's times through here by 5 cos theta. So if we do that, what I get here then is 5y cos theta. I then have minus 5 sine theta times 5 cos theta. So what I get here then is minus 25 sine theta cos theta, like so. And this here then is equal to 3 sine theta times by x. So I get 3x sine theta. And then finally here we get 3 sine theta times minus 3 cos theta. So to finish with, then we get minus 9 sine theta cos theta. So minus 9 sine theta cos theta, like so. And at this point here, then we're pretty much done, right? Let's just simplify here and get it in the form that we gave in the introduction. So what I'm going to get here then is 3x sine theta. Let's subtract 5y cos theta off both sides. So on the left-hand side then, I'm going to get 3x sine theta minus 5y cos theta, like so. And let's also add 9 sine theta cos theta to both sides here. So if we do that then, what I'm going to get here is minus 25 sine theta cos theta plus 9 sine theta cos theta. Once we simplify that here, then we get minus 16 sine theta cos theta. Okay, like so. And there we have it. So this final line here then, this gives us the equation of the normal to the ellipse with this given equation here at the point P. So this here then is our final solution. And that gives us the solution then to the very last question here, question 2. And that actually brings us to the end then of this video here on tangents and normals to an ellipse.